Hello everyone, welcome to the Exam Ignite YouTube channel. Today we are continuing the series of electromagnetic theory videos. In that I'll be discussing Module 5. Module 5 deals with the Faraday's law of magnetic induction, integral form and the point form, inconsistency of the Ampere's law with the continuity equation, displacement current, conduction current, derivation of the Maxwell's equation in the point form and the integral form, Maxwell's equation for the different media, uniform plane wave where the wave propagation in the free space, derivation of the plane wave equation from the Maxwell's equation, uniform plane wave, Poynting theorem, waveform, the skin effect or the depth of the penetration. So this is a module 5. Module 1 to 4 are already uploaded in the channel, and please check the description box for those links. Starting with the integral and the point form of Faraday's law. As per the Faraday's law, induced EMF, which is equal to minus d phi by dt, that is magnetic flux linkage, that considered as equation 1, where E is equal to integration of E vector dot dl vector, consider that as equation 2. So here we are having a conducting loop in the magnetic field with the ds vector and n cap unit vector. Next, therefore, what happens here is integration of E vector dot dl vector will be equal to equate these two 1 and 2 equations minus dq by dt. Now ds is a small area, consider a small area. For that we are having b vector dot ds vector, where our ds vector is ds dot n cap. So therefore what will be the flux? Flux will be integration of s into d phi and integration of s into b vector dot ds vector. D phi by dt is equal to d by dt of integration surface integration of b vector dot ds vector, which is again considering a dou dv vector divided by dt ds vector. So putting this fourth equation in the equation number 1, that is our first equation, we get induced EMF is the transformer induced EMF, that is equal to minus dq by dt. Substitute this, that is in surface integral of db vector divided by dt into ds vector, which is my equation 5. So now by 3 and 4 equations, we get by this third equation and this fourth equation, equate those two. Here integration of E vector dot dl vector will be equal to minus integration of db vector by dt into ds vector. This is the integral form. So by the Stokes theorem, we know that integration of E vector dot dl vector is equal to surface integral of nebula cross E vector into ds vector. This is equation 7. So from the equation 6 and 7, on equating them, we get to know integration of surface integration of nebula into E vector of ds vector is equal to minus surface integral of db vector by dt into ds vector. So nebula into E vector plus db vector by dt is equal to 0. Nebula cross E vector plus db vector by dt, integration gets removed, is equal to, so nebula cross E vector is minus dou b vector divided by dt, which is our equation 8, and that is the differential point form. Next is modification of the Ampere's law to suit the time varying conditions. We know that Gauss law is given as nebula dot d vector is equal to rho v. Differentiate with respect to t, that is dou by dou t of nebula dot d vector is equal to dou rho v by dou t. So remove the nebula outside vector component and put the dou by dou t inside. You will get the equation 1. Now we know that by the equation of continuity, which is already discussed in the previous module, that is nebula dot j vector is equal to minus dou v vector dou rho v divided by dou t, which is an equation 2. From the equation 1 and 2 on equating, we come to know nebula dot j vector is equal to minus nebula of dou d vector divided by dt. Nebula of j vector plus dou d vector divided by dt is 0. That is my equation 3. Now Ampere's circular law is given as nebula cross h vector is equal to j vector plus dou d vector divided by dt for the time varying conditions. This is the derivation. Next comes Maxwell's four Maxwell's equations in the point form for the static field. In electrostatics, from the Gauss law, it is derived as nebula dot d vector is equal to rho v. This is the Maxwell's first equation. In the electrostatics, as per the property of electric field, E vector is equal to minus nebula v. That is, curl of E vector is equal to nebula cross vector E vector, that is minus nebula of cross with nebula V, which is the curl of gradient here is 0. So nebula cross E vector is 0. This is the Maxwell's equation for electrostatics. Then Gauss law for magnetic field is nebula dot B vector is 0. This is the Maxwell's equation for magnetostatics. Now from the Ampere's law, we know that nebula cross H vector is equal to J vector. Maxwell's equation in the integral form. Here flux d phi over a small area, that is ds, enclosing charges, d phi is equal to d vector dot ds vector. Total flux is surface integral of d vector dot ds vector. By the Gauss law, total flux over the entire surface is equal to the total charge enclosed. So from that we can write surface integral of d vector dot ds vector is equal to rho v into dv. Second thing is the Faraday's law is given in the integral form, that is integration of E vector dot dl vector is equal to minus surface integral of dou B vector divided by dou T into ds vector. It is my equation 2. And third one is nebula B vector is equal to 0, ds is equal to B vector dot ds vector. The total magnetic flux over the entire surface is integration of B vector dot ds vector. Net flux is 0. That is my equation 3. Now fourth one is Ampere's law, where nebula cross H vector is equal to J vector plus dou D vector divided by dou T, taking the dot product with the element area, that is ds vector, of a closed surface and integrating over the entire surface. For this equation, we get surface integral of nebula cross H vector into ds vector is equal to integration of S into J vector plus dou D vector divided by dou T into ds vector. Stokes theorem, we know integration of nebula cross H vector into ds vector is equal to xi H vector dot dl vector. Therefore, the integration of H vector dot dl vector is equal to integration of J vector plus dou D vector divided by dou T into ds vector. That is my equation 4. Next is the transverse nature of EM waves. So that will be discussed in the next part 2 video. Please do watch the videos and do subscribe my channel. Thank you.